On Friday, May 10th, my friends and I saw the northern lights were forecasted right here in Ohio. The spectacle was already visible through the light pollution, but we decided to go to the darkest park we could think of. When we got there, we weren't the only ones. Easily 100 people were scattered across the Lake Erie shoreline to view the northern lights. It was a beautiful moment to share with so many strangers, but it gave me a dumb question. What had to happen for the northern lights to be visible in Ohio? You might have heard part of the story, but there's a lot more going on than you may think. It starts with the sun. It's on a cycle, oscillating between periods of high and low activity about every 11 years. In December 2019, the solar minimum welcomed us into solar cycle 25. Peak activity for solar cycle 25 was expected to occur between 2023 and 2026. Meet AR3664. At 15 Earths wide, it's the largest sunspot group so far this solar cycle. Like all sunspots, it was born where the sun's magnetic field is most intense. Sunspots typically form in pairs connected by two ends of magnetic field loops. Due to the Lorentz force, charged particles typically follow magnetic field lines. This property causes the core of sunspots to be largely insulated from the surrounding plasma and cool significantly, making it darker relative to the rest of the sun's surface. Ionized gas travels along the magnetic field loops, forming solar prominences. As the magnetic fields bend and move, so do the glowing loops. Sometimes these loops can cross, and a phenomenon called magnetic reconnection occurs. The magnetic fields cancel, and the ionized gas is launched into different directions and explodes to millions of degrees in a few minutes, triggering a solar flare. Sometimes solar flares can launch unimaginable amounts of plasma away from the sun, called coronal mass ejections, or CMEs for short. On Wednesday, May 8th, the sunspot group AR3664 erupted with numerous powerful solar flares, including an X-class flare, the highest classification. On the 9th, the eruptions continued with two more X-class flares. These flares produce several coronal mass ejections pointed at Earth. CMEs can take anywhere from several days to as little as 15 hours to reach Earth depending on the speed. It's difficult to track coronal mass ejections, but some experts believe that earlier, slower CMEs were, quote, cannibalized by later, faster CMEs, resulting in a much more intense front of charged particles. Okay, now that the storm is in motion, let's turn our attention to the target. The Earth produces its own powerful magnetic field. This is what it would look like without outside influences. However, the sun's magnetic field and a constant stream of high-energy charged particles called the solar wind pushes the Earth's magnetic field into a split shape made of a protective leading bubble and a comet-like tail. This is our magnetosphere. Without it, the solar wind would strip away the Earth's atmosphere. Instead, when the solar wind bombards Earth, most of the plasma is deflected away in the bow shock, not unlike the bow of a boat. Some of the charged particles make it through, but are slowed down until reaching the magnetopause, the border between our magnetic field and the solar wind. Here, our magnetic field and the pressure from the solar wind are balanced. Plasma would rarely cross this boundary if not for a returning phenomenon. Magnetic reconnection strikes again. Sometimes, the balanced magnetic fields between the Earth and the Sun reconnect, and plasma from the solar wind leaks into the magnetosphere. The plasma particles, mainly electrons, are then rapidly accelerated along the Earth's magnetic field lines and fly to the polar cusps at up to 10% the speed of light down to the atmosphere. There, the energetic electrons run into and excite common atmospheric gases. These gases then emit specific wavelengths of light to return to a low energy state. Atomic oxygen emits green and red, whereas nitrogen molecules emit blue. So, is that our answer? Not quite. There's a problem. The solar cusps are always on the sun-facing side of the Earth. The lights created at the cusps are called day-side auroras. But the most spectacular auroras are always near midnight when the sun is furthest away. And that's not just because it's dark so you can see it better. There is more activity on the dark side. But why? From the top rope, for the third time, magnetic reconnection! Like on the day side, magnetic reconnection leaks charged particles into the magnetotail. As it does, the entire magnetotail can expand. This expansion pushes the innermost opposing magnetic field lines together. Eventually, magnetic reconnection neutralizes the innermost field lines. Ions from deep within the magnetosphere are accelerated up the field lines to crash into the midnight atmosphere. Alright, now we know how the auroras are formed, and just in time. Experts observed the solar flares and CMEs over the last couple days. Power grids and satellite operators are bracing for the worst. NOAA, the National Oceanic and Atmospheric Administration, has issued a G4 Severe Geomagnetic Storm Watch. It should begin any minute. Let's take that minute to talk about how we measure geomagnetic storms. NOAA's Space Weather Prediction Center, or SWPC, has magnetometer stations across the world. These magnetometers measure variations in the Earth's magnetic field relative to a quiet day. The variations are collected, averaged, and applied to a 0 to 9 scale called the KP index. 0 to 4 on the KP index is not significant. A 5 constitutes a minor geomagnetic storm, prompting NOAA to issue a G1 storm watch if one is predicted by solar activity. The bar tops out at a KP of 9, constituting a G5 extreme geomagnetic storm. At this level, according to NOAA, satellites could struggle with tracking and communication, and unprepared electric grids could experience complete collapse. Oh, we're out of time. Here we go. The cannibalized CMEs are finally crashing into the magnetic field. On May 10th, from 8 a.m. to 11 a.m. Eastern Standard Time, the KP index measured at 3. From 11 a.m. to 2 p.m., it was at an 8, as warned by NOAA's G4 Storm Watch. By the 2 to 5 p.m. window, the storm had reached extreme, at a KP index of 9. It won't drop back down below 8 for the next 24 hours. The power of the sun's plasma reshaped the Earth's magnetic field. The magnetotail squeezed together, launching electrons toward the night sky. As the extreme storm squeezed more, the field lines were pushed further from the poles. Auroras could be seen as far south as Florida and Texas, including where we were in Ohio. The severe geomagnetic storm was the most powerful seen in 20 years, but it did little damage. Instead, all the complicated physics and phenomena did was provide hundreds of millions with a spectacular light show.